So let's continue. Our second speaker today is Professor Leopoldo Zayas from the University of Michigan. And today we're happy to have Professor Pando Zayas to tell us about logarithmic corrections to the entropy of AdS black holes. Let's welcome.
Right, so thank you. It's a pleasure to be here, and I congratulate the organizers. This is an amazing experience, an amazing workshop. So here's my talk. I'll talk about log corrections to the entropy of AdS black holes. In principle, it's a little technical. There's some technical steps, but I hope that you come out of here with some idea of some of the progress that has been taking place in the last few years. And some of the things and topics that I will touch upon are really related to some of the prizes that we're given in the Congress. So I think that this could be a nice talk. So my intention is not to make a seminar, so super technical, but by all means, I'm still here the whole week, so I'm happy to talk. All right, so let me start with my sort of standard spiel about why would you want to do this. So GR is great, of course. There are many experiments, etc. But as theorists, we want to understand quantum gravity. This was something that David Gross highlighted in his talk. So I think I don't need to motivate that any further. But there are things that we know in GR that we need to understand better, singularities, be them black hole or cosmological. And one place to start understanding better the theory is, of course, black hole entropy. That's, as we know, black hole entropy is a nice bridge between the micro world and the macro world. And we expect that this will be very useful as a target to understand it better in our search for understanding quantum gravity. But of course, maybe many of you were not born at that time, but for us old people, we are very proud of this Strominger buffer result. It was one of the most powerful results in string theory, where there was a statistical interpretation of the entropy of an interesting class of black holes, flat space. So that's one of the obvious achievements of our field. And just to put things in perspective, what I want to tell you about is about some developments in which I have participated that answer the similar questions in the context of the AdS-CFT correspondence. So basically, we want to understand the entropy of black holes that are asymptotically AdS and give them an interpretation. And of course, if you go back to my talk, I'm going to focus on some logarithmic corrections to that entropy. All right? So why do I want to look at logarithmic corrections? So of course, the idea here is to go beyond the leading order. So once you had success at the leading order, you match the leading order of the entropy we know is the area divided by 4G. Once you match that, you're very happy, but it would be nice to understand some corrections to that formula. So you have an observable, you see let's say the big chunk semi-classical piece, and then you're interested in some quantum corrections. So that's why I'm interested in these log corrections. I want to emphasize that, of course, this is at the level of sort of high school colloquium. I would say that this is a little bit like the hydrogen atom. You can get the energy levels correctly, but thinking completely wrong about the atom, thinking that there's some planet that goes around some other planet, etc. That has nothing to do with the physics. That's, of course, is not a good explanation in this conference. But in this conference, I want to highlight the talk of Matthias. So Matthias had two systems that were very good candidates for dual, but you need to do some dynamical computation to really pin it down. So symmetry will take you so far, and after that, you really need to go into detail. So that's a little bit my main motivation to understanding this. So this big chunk, maybe we can get by symmetries of the problem, but not necessarily understanding the underlying degrees of freedom, the dynamics. And that's why this is a good quantity. So as I said, maybe I clarified that there are two kinds of corrections to general relativity. Some corrections come by thinking of GR as a effective field theory, and these are higher curvature terms. There were some talks that address that. But I'm here interested about these log corrections, and these are one-loop corrections, fields that are massless from in loops, and they lead to this kind of correction. So What I'm going to be talking about is about this coefficient A, essentially. So I'm going to compute this coefficient on both sides of the correspondence, on the field theory side and on the gravity side. So luckily, I'll give you some of the reasons why this is a good object and why it makes sense to compute, to do loops in a quantum theory of gravity. All right. So that's what the talk is about. So the hero of the talk is this coefficient. So I'm going to, as I said, look at this coefficient from the two sides of the correspondence and make sure that everything is checked. So in a sense, as I said, I'm kind of like a logarithmic police. So people have declared that they have so much, and I, as a logarithmic police, I go and check this number. Is this number right? Then you're okay. All right. So that's what the talk is going to be about. Now, I want to make disclaimers, right? Because one of the problems of our field sometimes is that we like to claim big things. So I want to just tell you, these are things very matter of principle. These are very small corrections. So if you have a black hole, solar mass black holes of 10 to the 77 entropy, we're talking about the 77, right? So we're talking about a very small thing, but it's a matter of principle for us. So it has no astrophysical relevance or anything, but it's important that I want to just make that disclaimer. Now, another perhaps more conceptual is that, as you see, I'm going to explore this by looking at semi-classical gravity and quantum field theory. But I should have done this also in the quantum field theory if I could, but I can't. So I just I do what I can. I cannot answer the question in intrinsic quantum gravitational degrees of freedom, but I can answer this using a field theory. So I'll do that, but it's not the real thing, right? The real thing would be to do everything in gravity. And then, of course, I use supersymmetry, I use AdS, so this takes me further from the truth, but I just want to say the disclaimer, all right? So with that, now a little bit of as I said, I told you this log captures some interest in physics, but if you are a more hardcore person, you can say, well, people have been trying to quantize gravity for many, many years since the 50s. There are always these divergences, all these kind of problems. So I will convince you, this is the part where I want to be a little bit technical. I will convince you that this coefficient A makes sense even even if all that is true, if there are divergences and all that, okay? So that's why, so in fact, here I'm stealing a title of one of Ashok Sen's reviews. It's an IR window into UV physics. So this coefficient is powerful because it can be determined completely macroscopically. So you have a theory, and there's some massless, very low energy particles, massless particles. That's sufficient to compute that number, right? Now, that number also has to come from the full quantum theory, and that's why Ashok Sen, who was one of the pioneers doing this computation for asymptotically flat Strominger-Buffer black holes, has his very interesting review called this. So this is a very specific number, a specific window into what UV physics must do, all right? And so if you have a UV theory that you claim is the quantum theory of the black hole, this is like a test. So that whatever description you claim to have must agree with this macroscopic number. And this also, as I said, is used by Sen and collaborators to use precision computation in the Strominger-Buffer black hole. It was used also to clarify some microscopic realization of Kerr CFT by all these authors here, Strominger and collaborators. It was also used by Marcos and collaborators to compute some corrections to the free energy of ABJM on S3 and make sure that agrees with what you know from gravity. Well, sorry, the gravity agrees with what you know from the SAC. So in the case of ABJM, you can compute the free energy exactly. It's on area function. And that, if you expand this area function, you will find the coefficient that agrees with gravity. And of course, what I'm doing here is I'm going to tell you about how AdS black holes enter in this story. All right. So here's my outline. So first, I'm going to tell you, Here's my outline. So first, I want to tell you about some of these field theory computations beyond large N. Okay, that's the field theory part. Then I will describe the logarithmic correction on the gravity side, right? So this is in this. And so this is sort of like the main result. And then I'm going to discuss some puzzles that these kind of computations generate and how they get resolved in this context. I will also take some point of view, some clarifying point of view, some bottom-up. So I've been talking about top-down, 11-dimensional supergravity, etc. But at some point, I want to show you some of the details that clarify the structure of these coefficients from just 4D gauge supergravity. This part, if I have time, I will talk a little bit about of course, there's a prototypical example of AdS-CFT, which is n equals 4 super young mill. So I want to tell you a little bit about how those computations also fit in this framework, how to do those computations. Well, I cannot do them in the gravity side, but I have a way to do that. And after that, I'll finish with my outlook. So that's the plan. Any question? Good. So let's start by the field theory. So the field theory is this ABJM. I think this is Aharoni, Bergman, Jeffries, and Montesena. So it's a three-dimensional Chern-Simons theory with level K and minus K. So luckily for me, there was a very nice talk by David Tonk about this theory. So we know these are very run-of-the-mill, interesting for condensed matter people theory. This is actually, in my humble opinion, an advanced, this is a little better than the original computation of Strominger-Vafa. You needed to know a lot about the brain, so very complicated degrees of freedom, very complicated structures, modular space of instanton. So here, all you need to know is kind of condensed matter, standard 3D theory. Okay, so there's matter in the fundamental. Here's the quiver. I don't want to go into a lot of details, but essentially, the theory has some global symmetries. It preserves supersymmetry depending on this value of K. What I'm interested in computing is the partition function. I want to count states. Of course, I need to compute the partition function. This is, of course, a specific type of partition function that supersymmetric. So you see the -1 to the f to count bosons and fermions with different sign. And then, of course, I told you I have a large global symmetry, so I can decorate my partition function with those. And then these counts have BBS states annihilated by this supercharge. So the Hamiltonian here is given by anti-commutator of QQ bar. These are generators of flavor symmetry. Right, so I in principle could just, if I knew all the states, I could just enumerate and construct my partition function. But what one ends up doing here is to use the fact that this partition function can be computed using path integral with appropriate boundary conditions on the topological twist on S2. So this was established by Benini and Zaffaroni, and that's essentially what we're going to use. I want to use, so I've been talking about this field theory on S1 cross S2, but in fact, the computation on S1 cross an arbitrary Riemann surface of genus G is almost immediate, and it's impressive for me to present results that are true for any Riemann surface. All right, so here's a little slide about supersymmetric localization. I see very few students, so maybe I don't go into a lot of details, but essentially, if you have supersymmetry, and that was one of my disclaimers at the very beginning, so if you have supersymmetry, you will have some supercharge, so you can always modify your action by some Q-exact operator. The action, the value of the path integral is independent of this parameter lambda, so I can compute it at lambda equals 0, which is what I wanted to compute, or at lambda equals infinity. But at lambda equals infinity, this simplifies incredibly. So all configurations that contribute must be in this locus, QV equals 0, and then all I need to do to have the exact answer is to compute the one-loop determinants. All right. So this is again, of course, this idea came to physics from mathematics, but is now a standard way for us to compute. So the partition function that I defined at the beginning, we can compute using some path integral, and then using further localization, it boils down to something that is going to be a finite dimensional matrix integral. All right? Yes. V is some fermionic operator that is in the theory that I can construct. Okay, I can be more careful. So the whole thing has to be a positive definite for this to converge, etc. All right, so let me briefly describe. So this is my background, S1 cross S2. Then there's a background R charge that implements the twist, right? I've been talking about this topological twist. The answer is going to be presented in this form. It's a little bit like Lego pieces in this kind of localization computations. So this Z int here is a meromorphic form, cut-time valued complex variables that are defined here. They come, of course, from the UN and UN. Then there's a lattice of magnetic fluxes that we must sum over. All right, and then of course this int is the classical part times the one loop, and we know this for well, the classical part is just the evaluation of the Chern-Simon action, and the one loop can be computed like this. U is part of the part of the gauge group. All right, so again, I don't want to go into a lot of detail. This is a very well-established piece of physics. One can just apply it to this problem. The answer is here. It looks, again, my goal is not to show any details, but to convince you that this is well understood. So you see that these are essentially generalizations of essentially any counting problem, or most counting problems have to do with factorials. These are fancy factorials in some sense. And this B matrix is because it's a technical part. Oops. Yeah, it's a technical part. This B matrix is because it's the Jacobian of some coordinate transformation that you do. Again, I don't want to make you think about this in a lot of detail, but this is a well-defined problem that you can solve. The integral, again, localizes, or the answer comes from evaluating some poles of an integral. There's a prescription for how to go about those poles, etc. So this is all well understood. Here's my summary slide of the localization. So the summary slide is that I have, please. I'll show result. Okay. So you want to see the Larsen limit of this? Okay. No, these models. So these models might admit a giant graviton expansion, but this is not what I'm doing right now. I have the partition function exactly, but as a solutions, I have to look at the space of solutions of these Bethe equations. So this finding the solution to this system, I can do it. I can do it numerically. I can do it, but it's not simple. So it's not. Right. So these are, okay, I didn't write the equation. Well, yeah, I did write the equation. So these two things must be equal to 1. These are the Bethe answers equation that solve the localization problem. People know a lot about large giant graviton expansion if you have gauge group UN. So for product, the story is not so simple. But I'm happy to talk more about this because I'm very excited about giant graviton expansion, and I'm working actually on that currently. Good. So what I wanted to emphasize is that at the end of the day, I have these equations. They are not trivial, but they are nevertheless a system of 2n by 2n equation. And then you can have some very smart undergrad student help you solve the system. So the algorithm is very simple. Solve this system, plug back into your partition function, and then you have it. And you have it exactly in n. So it's not a large n approximation. And that allows me to explore not just the leading piece, but also subleading pieces, which I do in this slide. So here in blue is the leading piece of this partition function. Okay, remember these were fluxes, then there are some chemical potentials that I introduced. I don't care about these other terms, but the term that I was looking for was the coefficient of log of n. So n really is, well, you have to think about a scaling of charges, but this is the 8 that was at the beginning of the talk. Again, this leading term reproduces the Bekenstein-Hawking entropy of a streamal AdS4 cross S7 magnetically charged black hole, where the magnetic charges are given by this N. And this is a new term that is the log correction to the entropy. So these are terms that you can study. That's Zhenbing. Yeah, these are terms that you can study. In fact, more recently, I think that Bobiev and collaborator have been able to clarify this a little bit more. These are some higher curvature terms that you can also pin down, but that's not my thought. All right. Good. So these terms. Oh, sorry. So these terms are also known. So maybe let me. Good. So currently there's so this is all known. So people have been working. So we did this in 2017, but the state of the state of art is, for this problem is that now we understand a lot of all these subleading terms. In some cases, they can be resummed, and they also give you a nice picture of shifting the area function that Marino and friends obtained. So this is, but I don't want to push that idea, that direction, but this is essentially what, Nikolai Bobiev and many collaborators have been very carefully doing numerical analysis on these expansions, and they have convincing evidence, let me say, that that you can resum all this, and they amount to shifting some arguments in area functions. They do some of the higher derivative correction, but not all. Any other question? Yeah. So this is this. Yes. Um, yeah, I'm sorry, I did not fully. So what was what is the main problem that you see? Maybe you can repeat. Just repeat, please. Okay, good. So again, in some other cases where I understand the index much better, I find at n, I can check this thing, but this is an approximation very large n. So I'm taking the leading terms in that n expansion. So if you want to see the discrete properties of the index, like the ground state, or if that's what you're asking, then I need a much better control. That I have in some other cases. Maybe for AdS 5 process 5, we can get back to this question. No, yeah, please. Yes. Yes. Okay. Yes. Okay. Okay. That's good. So no, I think I'm computing an index. So there's -1 to the f in this sequence. So I have all my chemical potentials turned on. There's a constraint I have to meet, but I also have these magnetic charges. So this is some sort of, if you want, maybe mixed sort of ensemble index if you want. So that might be the question. But I'm happy to discuss more because right now I'm being a little bit slow. Sorry. All right. So this kind of computation I explained for ABGM, but I can do it again with one of my former students, Yuxing. We can do it for many theories that are asymptotic. They have duals that are, okay, so the dual of the theory, so if ABJM had dual AdS4 cross S7, these theories have AdS dual AdS4 times, these are 7-dimensional Sasaki-Einstein manifolds. For these manifolds, we know the quiver very well, so we can just look at the field theory and compute the leading, Amsel leading order, and for all of these quivers, we get the same answer, all right? And good. All right, so that's the end of the field theory part. So I have computed the topologically twisted index for a lot of 3-dimensional field theories. For all of them, I have the leading piece, and the subleading piece is minus a half log of n, which is what I want. So now I want to go and solve that problem on the gravity side. All right. So on the gravity side, I'm going to first discuss the this M2 branes. This is the case of ABJM. So the index was computed in ABJM with topological twists. So there were these fluxes on S2. The fluxes translate on the gravity side to magnetic flux, essentially of the theory, magnetic flux on S2. So I'm going to have a background. So again, I should honestly do this in 11 dimension, but just to simplify my writing, I am going to focus on the 4-dimensional part of the metric. So I can think of these theories, if you want, as on some n equal 2 gauge supergravity with this prepotential. All right, but it's not important. It's just a way for me to write the theory. So you can see that these are basically a stream of AdS4 black holes, and they have a magnetic charge. So this is the background. What I need to do, I have a gravitational background. Now what I need to do is to fluctuate the fields of my theory around this background, and then compute the one-loop correction to the effective action. All right. So no. No, these are all supersymmetric black holes. These are extremely supersymmetric black hole with magnetic charge. No, but there's no singularities that I can think of. This K of A is the Keller potential that is attached to this theory. If I look at it in this 4-dimensional language, it's a little bit of a language. So the physics is really here. So you can see that for large R, this becomes AdS4. There's some R for which there is a horizon. That's essentially what I wanted to highlight. So and then there's this magnetic fluxes. All right, so this, just to see, so the entropy of these solutions, area divided by 4G, contains, again, this Keller potential, but it's given by this function. And look at, so these functions are really quite complicated. So that's what I want to emphasize, that what Benini, Christoph, Zaffaroni did was quite non-trivial, right? So you might have already been convinced that this is the right duality, but so at leading order, this is the blue formula that I showed you at the beginning. This is quite an impressive agreement between the entropy in field theory and the entropy on the gravity side. But again, my goal is to do one-loop corrections around this and see what happens to the log term. All right, so again, I sort of explain, I have a background, I fluctuate my fields, small fluctuations. So when I integrate those, I essentially have my one-loop effective action, which is equivalent to computing some determinants. In this background, determinants I'm going to compute as usual, using these are the eigenvalues, so I don't consider vanishing eigenvalues. And then, because this is a computation in gravity, you want to preserve, if possible, diff invariance, so you use this Higgs-kernel approach. Good. So now this is this and the next slide are the two key parts to convince you that this result makes sense in gravity, where there might be many complicated divergences, etc. All right. So bear with me for a second, especially if you're a student. This is a good message. All right. So the Higgs-kernel that I use to compute my determinants, it contains both the zeros and the non-zero modes. That's sort of a fact. So when I'm computing this, the one without zero modes, I need to subtract them. So this is what this Na0 is doing here. It's subtracting the zero modes from the heat kernel because the heat kernel brings everything together. That's step one. Step two, the heat kernel itself admits this nice silly DeWitt expansion for a small proper time, if you wish, tau. And so the silly DeWitt expansion is essentially written down here. These numbers, AN, are coefficients combination of Riemann tensors, so they are also well understood. And just to give you some intuition, if I am very close to flat space, my eigenvalues are just sum of momenta, and I do this Gaussian integration, I get this T tau to the minus D over 2. So A0 is something that is like an expansion. The whole thing is an expansion around flat space, very high energy. That's what this subject is doing. All right. Good. So now, the other important thing is that I'm looking on operators that are going to be like Laplace operators, some kinetic operators. They are themselves, they scale with the size of the space as L to the minus 2. So it makes sense for me to take this proper time parameter and rescale it. When I rescale it, I put the expansion and my rescaling. So now you see that the only place in which I can get log of L after integrating this is when this is 0, right? So I'm integrating over tau bar. This has to be 0 for me to get a log. That happens for n equals d over 2. So essentially, in this whole large silly DeWitt expansion, only one term can contribute to. That's what makes it robust, because you might have many complicated things going on in your full determinant, but the log can get corrections only from this term, right? And now, the cherry on top is that if I'm working in odd dimensions, there's no way for me to put the Riemann tensor together in a way that this A d over 2 is non-zero. All right? So I said everything. So now let me summarize. So first, this computation is very robust because I can change my UV cutoff, and the coefficient of the log cannot change. The coefficient is insensitive to this cutoff. So that's, oops, sorry. So that's good. And then on top of that, in odd dimensions, the log can only come from 0 modes or boundary modes because there's no AD over 2 that I can form in odd dimensions, just from diff invariance. So what I wanted to compute in 11-dimensional supergravity, which happened to be odd dimensional, I want to compute corrections to the one loop correction to the entropy. So I end up getting contribution from the 0 modes. There might be some ghosts that I will treat. Sorry. There's the operators that I include without 0 modes. Then there might be some 0 mode contribution that I have to include. And then for these kinetic operators that I mentioned, I might have bosons and fermions. Okay, that's the whole argument. That's the technical part. So now all I need to do is to tell you just details of this computation. But the physics is here. I'm in 11 dimensions, so the silly DeWitt cannot contribute. The only things that contribute are 0 modes, and whatever the answer, it cannot change as I move my cutoff in the theory. That makes it safe with respect to the divergences we see in here. Yes? Okay, so yes. So there are logs that come when I change the ensemble. There are logs that I'm thinking maybe I start in grand canonical, and yeah, that is all correct. All right, so now, again, we are in 11-dimensional supergravity. The fields that are in that theory are the graviton, graviton, the three-form field. So the structure of logarithmic corrections, again, will be like this. This beta is essentially the term that I have to so I subtract the 0 mode, and then I add it as it should be added. So with appropriate measure that I compute with this beta. And then there are correction from ghosts. If there are ghosts, of course, in gravity, there will be ghosts. The point is if they can contribute. Now, I want to quantize this three-form in 11-dimensional supergravity, but to quantize this, I need to introduce, because this is gauge invariant, right? I can do D of a two-form and nothing changes physically. So I need to introduce this to form as a ghost, right? But again, I have a two-form. That two-form has some gauge invariance. of D a one form. So I need to introduce a one form. So this story was very nicely described in the 80s by Warren Siegel. It's called Ghosts of Ghosts, right? So I have some P form. It has a P minus 1 gauge invariant, so I need to fix that. And then it has a P minus 2, so I need to keep going. So it's a complicated thing, but it's understood. And now facts about AdS4, it admits a two-form zero mode. This is known from Camporesi Higuchi. And so now to quantize the three form, I can see that it can, because of the manifold that I discussed, S7 doesn't have first Betty number different from zero. It cannot decompose into a two form and a one form. So AdS2 does have a two form, but it cannot enter here, but it can enter in the two form ghost that I need for quantization. So that's how this enters. So good. So essentially what I need to do to compute how this two form contributes to the one loop effective function is to find what this B2 means. This B2 means that I need to very carefully understand in the path integral properly normalized. Remember, all this problem is a little bit like a scaling problem. So if you're thinking, maybe you're computing anomalies, you're almost right, because all I'm doing is understanding how the path integral changes when I rescale a particular size. All right. So in this case, the way to add a zero mode that comes from a two form is this beta equal 2. I put this beta equal 2. I count how many zero modes I have in a Riemann surface with genus G, which I told you I will use because it gives me a little bit bigger class, and I get this answer. This answer precisely agrees with what we had from gravity. And then, of course, what we have for field theory. And here I'm using this G is because instead of S2, I now immediately plug in a Riemann surface. So, okay, for the entropy, all I need to do is go to this, basically use thermodynamic relation. And this is roughly what I was saying. So I do get perfect agreements between the gravitational computation and the field theory computation for the log. All right. So this was for ABJM on an arbitrary Riemann surface. I can go back to the computation that I did for arbitrary Sasaki-Einstein, and there, in all my computation, it was important that there were no one-form zero modes. And there's a theorem that guarantees that there are no one-form zero modes in this Sasaki-Einstein. So they all have first Betty number greater than 1, greater than this 6m squared. So I now see that why these whole families of AdS CFT dual have log corrections that are precisely of this form. So that's sort of like the main result that I was advertising at the beginning. So here there are no boundary modes. That's a very good question. I might talk a little bit more about that, but here this is the computation. All right, so okay, good. So maybe I stop here if there are questions. This is a good, now I'm going to go into all the models that I can do, and of course I'm here because most of the results are positive. But the physics and the main example ends here. So let's say if you have questions, I'm happy to try to do my best to answer. There's probably a larger class. There are some that are non-toric, etc. But then for those, I don't know what the quiver is. It's not so clear. So I haven't studied those. I have studied a different class that I will discuss in the next slide. But for these 7-dimensional spaces, this is what I in fact, yeah, okay, this is what I know. In fact, there were some interesting questions for expert. I think for this Q111, there were 2 proposals for the dual by different groups, and but luckily for me, either proposal give me the -1/2 log n. So at that point it's okay. Yes, okay. Give me 3 or 4 slides, and I will show you what happens. It's a very interesting question. Yes. Yeah. So if there are no further questions, so let me show you. There's another class of theories of AdS4 CFT3. They come not from M2s, as I described. This is what I described, right? These M2s are cones on probes on the cone over segregation 7. But there are other classes that I can construct AdS4 backgrounds by considering M5 branes wrapping a hyperbolic 3 manifold. And for those, we also understand the dictionary. So here's a table, but for me, the most important thing is how n scale. Remember, I'm kind of just following the police of scaling, right? The log correction. So I see it scaled with n differently in two papers, one with Dongmin Gang and Nakbu Kim, and another with Francesco Benini, who was here last week, and Dongmin Gang. We have done this computation using the 3D correspondence, and we obtain the correction to the partition function. And this is in the field theory side, and I will show you now in one slide, since you are an expert in log corrections as I am, that the answer is the same. All right, so there's a contribution that comes from the 2-form 0 mode that I needed to quantize the 3-form 0 mode, and that gives me this. But now, because this manifold, these hyperbolic 3 manifolds typically have 1-form 0 modes, they have first Betti number non-zero, I can have now 3-form 0 modes contributing. They will contribute like this. So there's an overall negative sign. Oh, sorry, there's the ghost had a sign difference. So, and then if I do more or less the scaling that I mentioned, I subtract 1, and I count now the numbers. I have the number of these 3-form 0 modes is the number of 2-form 0 modes times the number of 1-form 0 modes, and then I add all together and I get success. So this also works. So this worked for all AdS4 that came from M2 branes, all AdS4 that came from M5 brane as well. All right, so now I want to talk a little bit about a puzzle, and this is related to Jianbing's question. So I started praising Sen, because Sen is for many of us, is a great guru of string theory. So I started saying, so Sen introduced something that was called the classical entropy function, and it was very powerful because it was a way to understand wall entropy. So all higher curvature corrections were put together in one nice story, which is this classical entropy formula. And it was correct, in every case. Now, if you want to apply this classical entropy formula in AdS4 and 5, that was done in these papers, including Francisco and collaborator, Francisco Morales. So it also extend there, no problem. But on top of that, Sen has a quantum entropy formula. The quantum entropy formula does tell you, go to the near horizon geometry and do your computation there. The near horizon geometry of these theories is AdS2, process 2, or cross-on Riemann surface, and that's what Jianbing was asking, whether I have boundary modes there. All right, so the question is, since we reproduce the answer using the full AdS4 and not this region, so what's going on? That's really it was a puzzle to me. In fact, so let me show you that if I go to the near horizon, I get the wrong answer. Well, I get an answer that doesn't agree with what the field theory is doing. So near horizon, the geometry is AdS2. I said S2, but it's really an S2 bundle over S7. So it's this M9. And here we can also know how to do this counting. So there's a 1 graviton in AdS2. There are fields corresponding to Killing vectors in M6. There's a 1-form 0 modes also in AdS2. This is a theorem of, again, Campuresi Higuchi. In any AdS2M, it admits an M-form 0 mode. So this is the 2-form for AdS4, 1-form for AdS2. But these are there. And now all I need to do is to put together the contributions. They come from the graviton, gravitino, 3-form, and 1-form. And that's the answer. This answer does not agree with the -0.5. And this actually, Intact Jian, who's now in China, and Lal obtained the same result. So we were a little bit confused, and maybe we made a mistake. But so Intact was a student, I think was postdoc Sen. So we have a stamp of approval. This answer is correct, but does not agree with what the field theory is saying. And of course, what we tried to clarify later on was what to do now with Sen's entropy formula in the context of AdS. All right, and that's now what I can describe to you. It's a paper with my ex-student Marina David and Victor Godet, and I own the graph from Michigan. All right. So that's the puzzle, that if you go to the near horizon, as you were prescribed before for asymptotically flat black holes, the counting does not seem to agree. So what here is where I'm. So here I want to take, as I said, a bottom-up, sort of bottom-up approach. I'm going to be in 4D gauge supergravity. Then the contributions to log corrections come from local terms. These are the ones that come from silly DeWitt coefficients. And then global terms. These are zero modes, boundary modes, etc. All right, that's sort of my explanation here. The local is the silly DeWitt. And of course, so the first silly DeWitt coefficient you can expand in some basis of this higher curvature term. And in this paper, what we did was to study this question for all, well, for some fields, but also for some theories. And we obtained some interesting things that the community was not expecting. There was some idea that this could be, that the answer could always be sort of topological, kind of like the Gauss-Bonnet type of answer. But now we see that in AdS, that's not the case. Again, this table is sort of some intermediate step. We can now apply this answer to black holes like Rayleigh Nostrom. And one thing that we find is that the local, so here's an answer for the local part that I defined before. The important thing, let me summarize here, is that you can compute this log correction using the asymptotic geometry or the near horizon geometry. Now, the local part, the local part, right? The local part, or maybe here, the computation of the local part for an extreme of black hole, it can be done either in the geometry or in the near horizon. There's no difference. So in that sense, this is now understood from the bottom-up point of view. So the whole contribution really comes from zero mode. So it depends really. So all the local degrees of freedom that you evaluate, you could, as Sen explained to us, you could do in the near horizon, you can do in the full geometry. There's a nice paper that is called black hair removal, etc. What we know for a fact is that the field theory captures everything. So now the question is how to go from the full space to the near horizon space. And what I'm saying here is that if you have zero modes, you have to be very, very careful doing your computation. Yes. Okay, this is not asymptotically flat, but okay, yes. Mm-hmm. Yes. Uh-huh. Yes. So good. So when I do my computations, okay. So for this computation, I really have one scale. I'm thinking mostly AdS, and then I have the Riemann. I have this combination of Riemann terms, and I have those depend on the background, and I evaluate them on the background. Mm-hmm. Okay, so I also get so many of the charges that I use in AdS black hole, I scale them with L appropriately. So like yes, I agree. No, because in field theory, you usually work in some, let's say, Cardi regime where you know exactly what the scaling of charges and chemical potential is. Okay. All right. So good. So and I was so this computation and at least understanding this difference, I think it has implication for this more recent computations about log temperature corrections to these theories. Of course, the theories that I have discussed are all supersymmetric, and they don't suffer. At least these theories have enough supersymmetry; they don't suffer for log temperature correction. But we see here that there's a difference. All right, so I have 5 more minutes. Maybe I'll tell you very briefly about similar computation in AdS5. There was actually these 3 groups are one of the awardees of this edition for the computation of microscopic entropy of AdS5 black holes. This computation has been extended to AdS4, 6, and 7. And now one question is, so when the Strominger-Baffa computation was done was very impressive, but then ultimately people understood that a lot of what's going on is really related to some 3D theory or some CFT2 that lives in the near horizon geometry. So we want to understand whether a similar story or mechanism is happening for these AdS black holes. And so what I'm going to describe very briefly, this is the superconformal index now for n equal 4 and s1 equals 3. It counts 116 BPS states. These are charges in SU4, charges and angular momentum. But this has been computed very carefully, and I can track what the log is. And this is a computation I did, former student Alfredo and Junho Hong and my colleague Jim Liu, and different approximations. So one is this Cardi-like limit, which is central for many of these computations. But we were also able to do it using a completely different approximation, Bethe-Ansatz. So it's similar to the equations that I flash for the ABGM partition function. But this coefficient is very robust. So we obtain the coefficient of the log in the same. And more importantly, perhaps, other groups reproduce this same result. Antonio Mariti and friends, even for other gauge groups. And then there was a paper that discussed an effective field theory approach to this computation, and again, obtained the same number. So this number is very robust. And what I want to post, maybe I will flash very quickly. So if I think of this AdS-CFT, I've been working at this level, but I can try to understand how much of this full correspondence I can capture by just looking at the near horizon AdS3 and using curved CFT geometry. So I will get some geometry. And this has been discussed by many people, also only here present, that these ideas of curved CFT apply to AdS black holes. In this recent paper with Jun Yang, who's in the audience, and Marina, we were able to discuss this for all the black holes that are in this list of things that we understand. And again, this is the picture. So we had some understanding of the entropy here, but how much can we understand from here? So I focus in AdS5 black hole. AdS5 admits being odd, admits no zero modes in AdS5. So this issue of where to compute becomes, for this black hole, not so relevant. And so what we are doing here is the computation using curved CFT. So you have some CFT2 with some U1 global charges, and you can compute the leading saddle point that will give you the Cardi formula, and that reproduces the index. But if you look at the one loop correction in this framework, okay, so you will get an answer that doesn't look like the log, but after you do the Laplace transform or Fourier transform, you will get the same answer. So now we have an explanation for the log entropy of AdS5 black holes, and also AdS5 rotating black strings. So they're the same. So with that, I can summarize roughly what I had said. It was a lot, but so we have log corrections of magnetically charged black hole in all this class of AdS-CFT dual. We also understand what happens in the 3D correspondence. AdS4 black holes that are obtained from N5 brain. I discussed a little bit this bottom up to clarify where the corrections come from, and the local corrections can be computed anywhere. And then I also talked very, very quickly about this AdS5 rotating black hole that includes also the string. From the near horizon CFT2, we are able to also check the one loop corrections. So I want to finish saying that, okay, we learned some lessons that separate AdS4 versus AdS5, and these are, of course, mostly determined by the zero modes. The degrees of freedom do not live locally at the horizon, at least for AdS4, you have to be very careful with the different zero modes. One open question that I'm very interested, but I have made very little progress, is to try to do the computation of log n directly in type 2b. So the computation that I explained to you used this curve CFT, and then I did some CFT computation, but it would be nice to do it directly in type 2b. So all this discussion about entropy was, of course, a statistical mechanical entropy. So I had some partition function, I counted the state, etc. This is still very far away from the conceptual discussions that have been going on in our field about the entropy as a more von Neumann quantum information theoretic object, and that would be nice to understand a lot better. One thing that is going on right now that is quite interesting is that, as I told you, that there's some physics that you can understand from the lower dimensional gravity. I mentioned curve CFT, but there's quantum aspects of JT gravity that are very nicely embedded in this picture. So many people have been working on this. Mukun wrote a very nice paper computing the thermodynamics of correction to the thermodynamics of rotating black holes. And I follow up with some students and postdocs in that direction, particularly because I'm interested in AdS. So this was for asymptotically AdS. You can also try to see in the context of AdS condensed matter applications of AdS CFT, whether this changes the phenomenology of some material. So with Junyan and a student, Xiaolong Liu, we discussed what happens to some aspects of the strange metal. We can also discuss what's happening at the level of Hawking radiation. So now that you have this new sector, boundary modes, etc., you can try to see what's happening there. I'm more ambitiously, we are trying to discuss with Son Yuan, who's in the audience as well, UA. So how to carefully recalibrate statements that people made about fluid gravity correspondence at very low temperatures in this context. So I have to mention one last direction that I like very much, which is, so we have seen a lot of gravitational physics of the JT type using directly from black hole, but it would be nice to see some SYK-like physics coming from the gauge theories that we have discussed, and that I have some modest progress with my collaborators, Mike Heidemann and Joaquin Turiachi. So with that, I thank you very much.
Yeah, so thank you for a nice talk. So DHS gave a formula for the one loop determinant in terms of quasi-normal modes, which also incorporates boundary modes. And I think these quasi-normal modes are exact for certain half VPS states, definitely exact for the near horizon geometry. So this is one way you can immediately get these checks on the log corrections and all that, right?
I guess so, but I'm not super familiar with I know the formula, but...
It doesn't work in many cases. So, like, for instance, if you don't know the quasi-normal modes, things like KER are completely out of reach, I think. But also KER doesn't have JT anything. So, in some cases, like Kähler geometries and things that look like products of SNs, those have exact quasi-normal modes. So the formula is exact up to some subtleties, I think. It's more like a comment, but I wonder if you can. I wonder if you can check what happens with the boundary modes using DHS.
My question, I have a confusion about the supersymmetry of the black holes. You have two parts. The first part, you talk about supersymmetric magnetic black hole at extreme
Yes.
And the second part, then you talk about the iron black hole with both electromagnetic. For the iron black hole, I think in the extreme limit, then it ceases to be a black hole. So you don't have a kind of supersymmetric iron AdS black hole per se. So the first magnetic black hole, supersymmetric AdS magnetic black hole, what theory is it must turn on some kind of hypermultiplet or something. It cannot be just the minimum supergravity. It's the solution to the minimum supergravity.
So this solution, this AdS black hole was obtained in STU. So I show you,
Inside STU.
yeah, I show you the
So the
prepotential.
simplest would be just a minimum gauge supergravity, right?
Okay, no, here you need, I mean, in fact,
You need to know
yeah,
the
there are
extent of
scalars and the scalars were non-trivial. I just didn't write any of that,
Okay,
but
so
yeah.
right. But the later example with iron AdS black hole, in that case, I believe you don't have a supersymmetric version.
So these are rotating
you,
black hole. These are rotating black hole without magnetic.
You
in the
have to
second
have
part.
a rotation, yes. Right.
Sorry?
Okay.
In the second part, these are electrically charged rotating black holes in AdS. And they
That is electric.
just electric, yes.
But you also you talk about the iron ionic black holes.
No. So the first part was just magnetic in
Right.
AdS4, and then indeed there are scalar fields, etc. The second part is just the things like the Swettich loop up black holes, this standard 5D.
What I do, give an example of that is
So that one was just magnetically charged in AdS4 process 7, if you wish. Maybe I'm happy to
I'll
clarify.
ask you.
Okay, let's thank our speaker again.